Okay. Hi, my name is Timothy Swan. I went to University of Illinois for my undergrad and almost finished my degree. I still have foreign language that I can do pretty much whenever. I studied mathematics and computer science. By the way, University of Illinois is actually a really good school for programming languages and formal verification. They're pretty much the best for those subsets of computer science. Um, so I want to create a second generation operating system. And there's a long story behind it, and there's a lot of reasons behind it, and that's why I have this text that I'm going to show you right here. So I'll just kind of start from the beginning, try to explain how it works, what it is, or the context of it at least. I'm not going to get too deep into the technical details, but I'm just going to give some background and explain kind of the general idea of what's going on. So the first compiler was written by Grace Hopper in 1952. Why does that matter? Well, just the date. Computers have advanced, computing in general has advanced a lot since then, and we did some things in the 80s, and we've used files and things like that since then. But a lot of things we still do are actually unnecessary and just there because of tradition. And in fact, that happens a lot. If you've never heard of it, there's a speech given by the professor who came up with nulls. He basically called them the $1 billion mistake. And yet, a lot of people do not recognize them as a problem. And yet, it was just copied from his theoretical, programming language that he was messing with as a professor into Java. And it turned out that shouldn't be done. It goes against what the purpose of type theory, and we have optionals and things like that instead. So that's just an example. But going on, here's a quote from Wikipedia. A compiler is computer software that transforms computer code written in one programming language into another programming language. Okay, so I'm saying that basically that is now currently unnecessary. Why? Because the program can be dealt with. The program can be dealt with in its optimal abstract syntax tree form rather than linear text. Now, this isn't like an absolute go for everything. Obviously, there's some, like hardware or something when you're talking about the very hardware level with graphics cards and things like that. I'm just talking about software development. So, pardon me if I sound a little high strung. I've had a lot of coffee. Okay, so so some people might say an abstract syntax tree is more complicated for a human to deal with. I would say no, that's not true. The terminal branches can be shown in any form desired. So basically the branches of your code at the end, like if you have an expression that's 5 plus 3 times 2 or whatever, you don't have to show that in a physical form of a tree. You can reduce that. That's up to the editor. That's up to whatever software you're using to display the syntax tree. But it doesn't mean the code structure itself in the form that you're dealing with it in has to be flat. It doesn't have to. It can be an AST, and I would argue that it's actually, when you look at the big picture, then it actually is easier to deal with that, because then you can use algorithms for refactoring and displaying and editing your code that can then filter things for you and basically work as a patch editor. You don't need Git patch editing. You don't need that type of stuff, because the type theory is supposed to be doing that for you. But we'll get into that later. So, for example, I can view and edit a sorting algorithm in either the context of strings or in the context of integers. And it can be the same exact algorithm. I'm basically parameterizing it with a type in that case. So I'm in here. That's an example of me, instead of using version control, and you might think that patch controls is going to come out, and it probably is. There's patch control software out there, but I'm saying that you don't even need that, because in this case, you're parameterizing it with a type, a functional type. Haskell programs define a subset of what the machine is computing. So if you're paying attention to the text, I'm on the fourth little paragraph thing here that I wrote. So for example, IO monads, etc. So if you don't know about Haskell or these kind of, super genius, whatever people think of them, abstract programming languages and things like that, they've been around. They're kind of abstract. They are general. The ideas behind them, if you're not aware, is basically they take advantage of certain things like pure functional programming, things like that. Haskell allows you to define a function, compute it once, and then you never have to compute it again. If you know what the parameters are, you could save it, or you could hot swap things, which basically means changing your program as you're editing the program. What's the problem with Haskell? Well, they didn't know how to do inputs and outputs. Well, it turns out that you don't have to, the programming languages that you're dealing with, or the mathematical logic system that you're dealing with, doesn't have to define everything that the computer is actually doing. It just can define something that you're trying to prove or something that you're dealing with. Now, the way that works with Haskell is when you have inputs and outputs, and you have a function that you might want to depend on something, well, you can have something that's an impure function, something that depends on input or has an output or something like that, and then within it has a pure function. So you can pass it, be it like a formalized 5 or something, when in reality the bigger function passes it a 5. That's an impure function because it gets the 5 from input. Okay, so what I'm saying is the Haskell language itself doesn't define those inputs and outputs. It just defines functions and how they work, and those just get reduced. And so what happens is with Haskell, you basically have something attached to your compiler, something attached to your interpreter, other than just the language itself. You have extra computing functionality which deals with that input and output and stuff like that. And then you have the Haskell language, which is separate and kept pure, and it's managed by that more general program. And so basically that's what I'm saying, is that it is a subset. Well, how do we take advantage of it? Is to contain everything that we need, because it seems to be very useful when it comes to types. But a lot of people have trouble dealing with it, because then when you define like a type, suddenly the expression for that type in Haskell or OCaml or languages like that could be very large. And then if you have something like Agda, where it's like really complex, where types have types, those expressions can get really complex, and then just editing this is like a nightmare, so no one really does it. It gets too complex for people to deal with. They don't know how to deal with it. It's not in the industry. Even Haskell itself is not really used by the industry. There's only a few hundred developers out there. Okay. So, but I'm going to try to make that simpler. So let's move on to the next point. It is better to have a language formally receive information from itself rather than text. Okay, so we're reading the fifth one here. For example, Lisp expressions versus reflection, or a C program using a compiler. So what am I saying? I'm basically saying a program that uses a compiler that compiles another program and uses that program. The problem with that is that you can't prove anything at the compile time of the outside program what happens in the inside program, basically. So what I'm saying is that like it's better just to use like Lisp S expressions, like a program should be able to it should be built into the programming language to use itself in that type of way. The problem is that even with languages that kind of have that functionality like Lisp, you have eval, and then people call eval evil because, well, it actually doesn't retain the mathematical properties. It doesn't prove what's going to happen within that function. So now it's really complex to try to prove what's going on where. So how does that work? Well, that's where I'm going to get into Coquen's calculus of inductive constructions. I'm claiming that that's basically going to solve that problem. So you don't have to worry about losing your mathematical properties. You can basically have programs within programs within programs in the proper abstract type of way, where you don't have to do any type of reflection or have Um, you don't have to have an eval. You don't have to use compilers at different levels of abstraction. In the case that I'm talking about, I'm making that claim that you won't have to do that to get whatever type of functionality. Not just functionality, because it's like Turing completeness. If you have a Turing complete program, theoretically you could do anything. But I'm saying, like, to get the abstract, clean working environment that you'd want with the ASTs, you still wouldn't need to go there. Is basically my claim. So I'm asking, why do you? Let's see, because yeah. So let's move on to the next point. The K framework. Okay, so this is University of Illinois. Roy Rosu, the professor there. He and other people made some formal verification of programming languages that exist out there, like C or Python, something like that. They're defined in text. And it's cool because they actually formally they use something called matching logic, which basically it works with the syntax and the semantics of the language so completely that you define the entire language in this logic system, the actual syntax of the language, and then you can simulate a program in this with this definition. So you can generate a compiler. You can have a formal definition of like Python or C, and then you can theoretically, if you do all the legwork, you can generate a compiler based on that definition for Python or C or whatever, just by saying, make me a compiler. So that's a really cool idea. In fact, I actually worked for this company for 6 months because I was interested for those reasons. Now, I only worked as a testing engineer because I don't have a lot of credentials, but that's what I did there. But the reason why I actually was interested in the company is because of this research, what the ideas behind it. But I realized that the company's more focused on existing program languages like C in this K framework, and I realized that the idea that I had is actually a little different. I'm going to explain that a little bit. So it's better to generalize on a type system and use code. I'm going to say I'm making the claim that it's better, instead of using K framework, to use Coquin's calculus of inductive constructions. This is a mathematician from France. He came up with this logic system initially in the 80s, and it uses the whole lambda cube. Haskell only uses 2 of the 3 parts of the lambda cube. This thing uses the whole lambda cube, and then it's inductive. So now you have that idea of reflection, or you could call it eval or something like that, compile time, runtime, and it's, instead of those 2 stages, it's expanded to n stages, basically. It's kind of like Agda, in a sense, uses this, but this is the complete logic system with all of it put together. So, okay. So why is it better to use that? Why am I making this claim? Because then any functional algorithm depending on another, so basically when you want to use an algorithm or a program that depends on another program, instead of compiling it and simulating another program inside of it that you don't know what's going to happen with that one, you can inductively infer the mathematical properties of another algorithm. And it's all the expressions are in that one logic system, so you can verify everything when you need to verify it, basically, which I'm going to say when you need instead of at compile time, because we're not really going to have an official compile time anymore. But I'll get into that in a second. Well, I guess I'll get into that right now. That's the next point. Notice that there results n stages rather than only 2, compile time and runtime. And then also on top of that, files are no longer necessary, but rather just metadata indicating whether an expression should be permanent. So whether if something should be saved on the hard disk or not is basically what it's going to come down to. Because what's end up going to happening is I'm going to create like basically a meta algorithm, which obviously doesn't matter what it's coded in. It could be in C or whatever. Just create a system that can reduce expressions, basically, which does all this. So sure, at that meta level, we could do whatever we want. We could use any language we want or whatever. We could compile, and it doesn't matter. We could use files at that level. It doesn't matter. But the point is that you don't have to. You can get rid of this. Eventually, you could just have an operating system based on this. You don't even need files in that. system. If you got this down, you just deal with your hardware, deal with your pointers and all that, and then just use this directly. So, in summary, you could say bye-bye to files. You could say bye-bye to compile time and runtime, because basically you'll basically be, depending on how you look at an expression, if you see it as value, it could be reducing that expression could be seen as running a program, and then editing the types for that expression could be seen as editing the program. But then you could edit the types of those types, and then that could be seen as runtime versus compile time of that one. So there, it is kind of a weird definition. It doesn't really apply. So you usually don't call it compile and runtime anymore at that point, because we're going to be dealing in that system, in this logic system, which is an inductive, and it uses naturals to count so that it's strongly normalizable. I'm not going to get into that, but basically it's proven to always reduce, which is one of the properties that you want if you want to deal with this in such a way that you get rid of bugs. You don't want infinite looping. Okay, so bugs that exist due to combining multiple programs, you can say goodbye to those, because basically everything will be one program, if you will, because we're kind of changing the idea of different programs using each other and sharing files or streams into kind of being functions of each other, or maybe meta functions of each other with types. So compiling and linking, goodbye to that, because who needs compiling and linking when you're always working with a syntax tree as it is, which I've already shown you can do with a simple programming language. I made an iPhone app called Inspiration Basic. It may or may not be on the App Store right now as you're watching this video, because I have to pay $100 a year for it to just be on there, and it's free, so I don't know if I'm going to, when it's on, when it's not. It depends when I pay that fee and whether I keep it on the App Store, but it's called Inspiration Basic. You don't need the containerization anymore, because you don't need to, how do I explain this one? Each expression, if you will, of your program it's already kind of, you can basically define its context. So you don't need like a special separate system that's designed to be like, well, this is a pretend separate machine, because we're formally defining all the context here, basically. So you don't really need containerization. That was just a thing to deal with the way 80s computers worked, I guess. I don't know. So you can say hello to pure functional programming. You can say hello to hashed reusable code, which hashed, so at the meta level, expressions can basically be hashed. You can have, for example, well, let's go back to the sorting algorithm. You can have a sorting algorithm that sorts depending on some type. Well, that sorting algorithm can be hashed with a generic type. So I can have a sorting algorithm that I write for ints, and then later on in my code I might try to write another one for sorting strings, and then it has the same hash, and it's just like, well, I already have a copy of this, and it's already proven to have such and such properties, and blah blah blah. So you don't need to reuse code. You can basically reuse code at different levels of abstraction and find it very easily, because it can all be stored in a database at a meta level. So you can have hot swapping. So you can edit. You're basically going to be editing. You're going to be changing a program while it's running all in one system anyway. So hot swapping is basically going to just be part of this thing, because the definition of interacting with or running your program is going to be essentially the same thing as editing your program too. So that's awesome. You don't have to worry about sitting there editing something and being like, okay, now time to compile and try it again. You don't have to do that. Auto refactoring algorithms. So refactoring is going to be totally different. Editing code is going to be totally different. Everything's going to be visual tree based. And patch control is essentially baked in. So in a way you could say goodbye to patching, but in a way you could say whatever patching was trying to do, it's already like here anyway. Like we use the type system to do patching. Like if you want to make two different patches to do two different things, you can just make a Boolean and then kind of filter your code based on that Boolean being true or false, and it will just show you the code based on whether that Boolean was true, for example. And you don't even, you just pretend that it's true and then edit your code accordingly. And then you can have a test that generalizes. You can step back from there if you really want to try to make things work for multiple patches in that sense. So the logic system is very different. It's more abstract. It contains like this weird meta step, because now you have induction on like the functions, but then you have induction like on the types. So it's kind of like a really super, it's like a logic system on steroids. It's crazy. But once you overcome the threshold of figuring out Coquelin's calculus of inductive constructions, you basically can do all sorts of crazy stuff. You can prove things. You can make programs that don't have most types of bugs. You can make really secure software. You can make really, really dependable stuff. So why am I putting this on YouTube? Well, it's a long story, but I've been studying this stuff. I'm 29 years old now. I had joined the military to pay for school. I went through school for the most part, and I used to talk about AI all the time before I used to want to, back in 2010, I used to want to I was just enlisted in the Army, and I wanted to start a company that made the AI for like quadcopters and stuff like that. So I've been interested in computer science like my whole life, but I've never, I haven't gotten to grad school. I haven't done PhD. I haven't really worked for a big company that's, trusted me or looked at me for ideas. I've never had enough resources to really start my own company. So I've just kind of been, I'm just someone who's been working normally, but also has studied this and wanted to do this my whole life. So I am just putting some things out there publicly and trying to maybe work with the public. I like how open source, how free software is done. I like the philosophies behind that, and I think that now in this day and age where you can get donations and things online, I can do some Patreon or something, or maybe I can put some goals out for a crowdfunding and say, if this amount of money is met, if this goal is met, then I will create this, and I will stick to whatever it is. I've always done it. I mean, I'm not going anywhere. I've been doing this for years. I've been working on stuff like this for years. When it cost me an arm and a leg, I probably shouldn't have even bought a car from my friend, but then when I owed him money back, I paid him back. And sometimes it takes me a while, but I don't go back on those things, But at the same time, I'm also scared to take a foot forward because of that, because I am very conservative when it comes to that. So I do want to come up with a realistic goal, something that I can do, and we'll go from there. I already made Inspiration Basic, and that was very important to me. That was a huge step for me, because even though it costed me to create that app, at the same time it helped me get some jobs. Even it helped me have confidence that I could do something like this. I could finish something that I started. So thank you guys for listening, and I will see you in another video. Bye.